Hello guys, Miss Williams here. Hopefully you just finished watching the ocean floor spreading video. So seafloor spreading, ocean floor spreading, whatever you want to call it, that is a divergent plate boundary. Now we are going to focus on one of the features that are made from convergent plate boundaries, so whenever the two plates come together. So this one is on mountains. There's several different types of mountains, and we've all been in the mountains. Most of us live in the mountains. Mountains are an important part of our life here, but what causes them? What causes the different types, and what other features are formed within the mountains? So mountains. One of the tallest ones on the surface of the earth, not the tallest one starting on the sea floor, is Mount Everest. And this is from a convergent plate boundary right here between India and China. So this boundary, there's actually 3 tectonic plates being pushed together here, but this mountain chain is only caused by the 2 coming together. So what is a mountain? A mountain is a large mass of rock or landform that rises a great distance above the base. So any land that is pushed up above seafloor, which is 0, probably no less than 300 meters, is considered a mountain. So where do they form? They generally form along convergent plate boundaries. So this is a collision boundary. And again, this wouldn't really look like this down here. It would look more something like the top, but that's fine. And it's just where their 2 are going together, and they're pretty similar densities. So they're not necessarily subducting like they would in the ocean, like with an oceanic and continental plate. So that's how we get mountains. And how do they form? They form from rocks that have been permanently deformed under stress. So whenever these plates get pushed together, these rocks are folded, they are pressurized. Sometimes you can have some contact metamorphism in there. They are basically deformed. So if you remember me saying anything about deformities or anything like that, this is an event that would cause those features. So what is the tallest mountain in the U.S.? Mount McKinley. So this is in Alaska, and its elevation is 20,320 feet or 6,194 meters. This is the largest one in the U.S. Again, we just looked at Mount Everest, which is the largest one on the planet that does not start at the seafloor. So there are 3 different types of mountains. There's folded mountains, domed mountains, and fault block mountains. And these are kind of determined by the features inside of them. So the first one is folded mountains. These are the type of mountains that we have. So this can be very easily seen whenever you're driving and you see the road cuts and you see these large folds or these squiggly lines, if you want to call them that. That's because these mountains were formed whenever the plates were pushed together. They weren't compressed so much, but they were compressed enough to get the little wave going. Kind of like if you had a blanket or a towel that was laid out and you pushed both ends together, you would get that little swerve there. So formed by the folding of rock layers during plate collisions. So something like this. You would have this at first. So whenever the 2 ends of the blanket or whatever would start to be pushed together, you'd get like a little fold. But then as that continues to be pushed together, that fold will break and it'll go over top and you'll get something more like this. And then as this process continues, this can happen again and again and again. Again, here's another picture of what a folded mountain can look like. So the different types of folds, they kind of go hand in hand. An anticline is an upward fold. So it would look something like this. And a syncline is a downward fold. So of course they're going to be connected. So we've got the anticline and the syncline. So let's see. Yeah, that's better. Syncline. So the anticline, the bottom's going to be up top. And syncline, the bottom's going to be on the bottom. So that's they kind of go hand in hand. So here in this image, remember, the anticline has the bottom up, so it's kind of like this shape. So right here is going to be your anticline in here. And if we look over here, it looks like we have the bottom of a syncline right here. So like I said, they kind of go hand in hand. And if we looked deeper and deeper, this would probably look something like this too. Because every layer of this rock is being folded like this. It's not just the one layer. So as you can see there. So the next type of mountain is a dome mountain. So one really good example of these near the East Coast is up in New York in the Adirondack Mountains. They're not as, they look similar to ours, but they're different whenever you look at the rock layers. So these are a circular folded mountain formed by uplift. So we have a folded mountain like we do here in our neck of the woods, but we have a little bit more of something going on. So we have the fold, but then it's also uplifted. So kind of like how the Appalachian Plateau, it has mountains, just like the Valley and Ridge region, but it's at a higher elevation due to uplift. So again, the dome mountain, you could have the folded features here or whatever other features, but it's being forced upwards right through here. So you're going to have undeformed rock, and then you're going to have your deformed rock. The next type of mountain is a fault block mountain. These can be seen out in the Sierra Nevada mountains. You can already tell these are much different than what we've been looking at. They're not as rounded, they're not as dome-shaped, they're not as rolling, they're more sharp and jagged. So if you recall, I think a few videos back or a few classes back, we talked about fault line. Fault line is just a point in the rock to where it's been broken and the two pieces have been moved. So in these fault block mountains, we have a lot of fault lines because they have jaggedly been moved or shifted. So this forms whenever normal faults uplift a block of rock. So the fault line occurred down here, and then these pieces of rock were then uplifted at different rates. So that's how we get all of these shapes as opposed to what we just saw in the last two. So again, here you've got your fault lines, and within these fault lines you've got the movement of the big wedges or chunks. And again, you've got tension pulling this way, and that's how you get these shapes. So in fault block mountains, it's not just one-way movement. There's several different types of movements that can occur. So as you can see in this picture here, we've got an uplift here, but then we've got an uplift here, and this is going down, and it's kind of different in each because all the fault blocks aren't equally distributed, and that's why we get the jaggedness. So another good example of the fault block mountains is out in the Tetons, out in Wyoming. Again, they're very jagged, they're very blocky, they're very big. They're not as rounded or folded as we're used to seeing in the other two mountains. So we've talked about faults several times so far. So let's talk about specific types of faults. So let's see. Faults are classified in 3 different ways depending on how the rocks on that fault are moving. So a reverse fault occurs when the hanging wall moves up. So the hanging wall is going to be this one, and this is the footwall. So a good way to remember that is you stand on the hanging wall and you hang on the footwall. So it's kind of like opposite. Stand on the hanging wall, hang on the footwall. So a reverse fault is whenever these two people in your little drawing get closer together. So it would be moving like this. That's a reverse fault. So your hanging wall is moving up and your footwall is moving down. Another way to kind of remember this is you can, whenever you're visualizing it more like this is the footwall. So when on this line, you're standing on it. This is the hanging wall. You would hang from this line. So you can remember it that way too. Now, for a normal fault, it's going to be the opposite. Your hanging wall is going to be moving down, and your footwall is moving up. So the bottom layer, or the footwall, that's being uplifted while the hanging wall is coming down. Which it doesn't, I always get them confused because I want to say the normal fault, the hanging wall is moving up, but it's not. Reverse fault is the one that has hanging wall moving up, and normal fault has a hanging wall moving down. So normal fault occurs when the hanging wall moves down at divergent boundaries. So reverse fault, convergent. They're coming together like that. Hanging wall moving up, footwall moving down, they're coming together for a convergent boundary. A normal fault happens at a divergent boundary. So we have the fault line in between the two layers of rock, and what happens is, as they pull apart, the hanging wall comes down and the footwall comes up. So divergent means a normal fault. What about a thrust fault? It's a little different. So a thrust fault is formed when compressive stresses act over great distances. So a thrust fault is a reverse fault. So it's a convergent boundary fault. But the fault plane dips 45 degrees or less from the horizontal. So it's 45-degree angle, which is half of a right angle, or less. So it could be a very shallow fault line. It could come like through here, but that's a thrust fault. So it is a reverse fault, but it's 45 degrees or less. So what type of fault occurs when rock on opposite sides of a fault plane move horizontally? Like this. We know that we called that a transform plate boundary, but the name of the fault is strike slip. I think I accidentally said that in the last video whenever I was referring to a transform fault, but it's whenever they go past each other like this, so it's a strike slip. So, Horst and Grobens. These are some technical terms for the wedges that I referred to earlier whenever we're looking at these fault lines. A horst are large blocks of crust that have been thrust upward. So your horsts are going to be these things right here. They are moved up this way. But a graben is going to be the pieces that are moving down. So right here, we would have the footwall moving up and the hanging wall moving down. So since the footwall is moving up, that's going to be a reverse fault. And the same thing right here. So these have reverse faults. But graben is the wedge that goes down. Horst is the wedge that goes up. So in this image here, we have the different types of faults. Down here, we automatically know what that one is. It doesn't move up or down. It goes side to side. So that's going to be your strike slip fault. And then here, this is the hanging wall. This is the footwall. So if we have the hanging wall going over the footwall, that means we're having two pieces of rock or land being converged or pushed together. So if it's convergent boundary and we have the hanging wall going above the footwall, that's going to be a reverse fault. But the question is it less than, equal to, or more than 45 degrees? Because if we look here, we have the same movement, but at a sharper angle. So out of the two different types of reverse faults, what is this one going to be? If it's equal to 45 or less than 45? Do we remember? If we go back, that is known as a thrust fault. So this is a reverse fault, but since the angle is 45 degrees or less, it's going to be a thrust fault. Now, again, let's look at the second one. The hanging wall is going up, and then the footwall is going down. So we know that they're converging. So that means that this is a converging plate boundary, and we know that that means it is a reverse fault. But it's more than 45 degrees on the angle, so it's just a reverse fault. It's not a thrust fault. Then let's look at this one. we've got the hanging wall going down below the footwall. So we know whenever we have that scenario, whenever the hanging wall is moving down and the footwall is moving up, that's a divergent boundary. So that gives us a normal fault line. And then, like we said a few minutes ago, this is a strike slip. So transform, reverse, normal, strike slip. I just called that up. I just lied to you. This is a thrust, a reverse, and a normal, and then a strike slip. I keep forgetting the word thrust. I don't know why. Okay, so we already know this. So we already know that we have mountains on top, and we have mountains on bottom of the seafloor. So top that means above seafloor. That means above sea level and below sea level. So we call these mountains seamounts, like mount for mountains, and then sea because it's under the water. And to map out these mountains, unlike on land we could just use planes and fly over and look at it that way. To map the seamount, we use sonar. So sonar makes 3D images, and we're able to map out the mountains on the ocean floor. When these seamounts reach sea level, though, they then become islands. So we've talked about the world's tallest mountain that starts under the sea, but the part that's over the water isn't quite as tall as Mount Everest. So that's on an island, though. So whatever breaches the surface of the water becomes the island. Okay, so talking about the different elevations of mountains and seamounts, that takes us all the way back to the beginning whenever we talked about topographic maps. So, just as a reminder, the circles here on a topographic map indicate levels of equal elevation. So this works above land, this works below land, all that fun job. And then this is just a pretty picture. These are most likely going to be they're not dome mountains. I think these are going to be more of your fault block mountains, these sharp-edged ones. So that's it for the mountain lecture. Please make sure you fill out those notes, and then I will have your day 3 stuff posted up in Classroom tomorrow. If you have any questions, just email me. If you have more questions about different types of mountains, email me that too, and I will get back to you as soon as possible. Bye, guys.